Hello, Math 1341 Calculus 1 students. This is extra practice for quiz 6, which covers optimization and indefinite integrals. This includes integration by substitution. So let's get started. This first problem is an optimization problem, and we are to build a fence that creates a 600 square foot rectangular enclosure against a very long wall. Well, let's draw a picture. Here's a wall. And then here will be this fence, okay, like this. Let's start labeling. Well, say this is X, that would make this X, and that would make this Y. Now, what else are we given in this problem? The very first sentence, in fact, this part, gives us our constraint equation. Our enclosure will have area 600 feet squared, and the area here is x times y. xy is 600. This is our constraint equation. First of all, it's an equation, and we're not trying to maximize or minimize area. This is fixed. We are trying to minimize the cost here. Now, we are given the type of fence that runs parallel to the wall, cost $1 per foot. So let's write our cost function here. Well, $1 per foot times y feet. This would give me the cost for this side. Then, next sentence, the type of fence that runs perpendicular to the wall costs $3 per foot. Now here you notice there are two of those sides, so we have 2x feet times $3 per foot. That would be 6x dollars. Let's just simplify this. My cost function is 6x plus y. And you notice this is my objective function. Right now it's a function of both x and y. The next step in these types of problems is you go to your constraint equation and you solve for one variable in terms of the other. So we have, say, y is 600 divided by x. Now I can write my cost entirely as a function of x, and it is 6x plus 600 divided by x. You notice this is really defined on an open interval. X, first of all, must be positive, and y must be positive. But this is the relationship between x and y, and no matter how big we make x, we could make a y. Wonderful. We want to minimize. We have a differentiable function on an open interval. Now we can look at 4 critical points. We take the derivative. Well, we have 6. Notice this is 600x to the minus 1. So when I differentiate it, I get minus 600x to the minus 2. This is defined on the whole open interval, so we can set the derivative to 0 to find our critical points. This gives me 6 is 600x to the minus 2. Let's see, I can divide both sides by 6, and at the same time I can multiply both sides by x squared. So I have x squared is 100. We really have one critical point. Technically, plus and minus 10 solve x squared is 100, but on 0 to infinity, we only have one critical point. So this is the only critical point. We are in this beautiful situation. We have one critical point for a differentiable function on an open interval. And so we can use first derivative test or second derivative test to make sure we have a minimum here. Okay, so let's verify. I'm going to use the second derivative test. Okay. Second derivative test. Well, we can differentiate again. You notice we have 0, we have plus 1200 x to the minus 3. The second derivative at this critical point is 1200 times 1, I'll write it this way, divided by 10 cubed. This is certainly positive. This says my function is concave up, so I can draw a little picture. Concave up. In fact, I do have a min. at x equals 10. Now, the final step of this problem, as we reread the question, we are asked for the dimensions that minimize the cost. So the x is 10, and the y comes here, will be 600 divided by 10. So in this case, the y is 600 over 10, which gives us 60. My final answer is 10 by 60. So let me underline this. This is what we are reporting back. This was this first question. Well, let's move on. Next optimization. In this case, we're to make a box with a square base. We're given a fixed amount of cardboard. Oh, and we have an open top. We want the largest possible volume of the box. Well, let's draw a picture. Here's my box. I can label X because square base, this is also X. And then we have some height Y. Now, this one's a little bit different than the last because volume, well, first of all, it's a three-dimensional shape, but we are maximizing volume and we have a fixed surface area. So the volume is X squared Y. And for this problem, this is my objective function. This is what I'm trying to maximize. Now, my constraining equation will come from the fact that we have 1,200 centimeters squared of cardboard. I can set 1,200 equal to, now I have to figure out the surface area of this box, but it has no top. That's important. So you notice I have one bottom, which will be an X squared. You see this height is Y. We have 1, 2, 3, and 4. They're all X by Y. Every side, X by Y. So there's 4 of them. We have 4 X, Y. And this is my constraint equation. It is an equation, and it relates the variables. We are not trying to minimize surface area. Say, it's given, 1,200 centimeters squared. Well, just like in the last problem, the next step is you use this constraint equation to solve for one variable in terms of the other. I think it's easier to solve for y in terms of x here. So first you notice that 4xy is 1,200 minus x squared. And now we can just divide by 4x. Y will be 1,200 over 4x minus x squared over 4x. 1,200 over 4 is 300. So I have 300 divided by x minus x over 4. Okay, this is my relationship between x and y. And at this point, I can write my objective function. I will call it v of x, say, because it is volume. I can write this entirely as a function of x. It's x squared times this, y. In order to differentiate, I want to multiply through by x squared so I can see the power on each term. So here you notice I have 300x, and then I have minus a fourth x cubed. Let's think about what this is defined on. Well, certainly x needs to be positive, and then we can stare at this equation. Let's see, y needs to be positive, which would say that x squared must be less than 1,200. So this goes from like this. 0 to the square root of 1,200. What are we trying to do here? We are trying to maximize. Fantastic. This was the hard part of this question. Generally with these optimization questions, the hard part is getting yourself to having a function of just one variable defined on an open interval typically, and then you're ready to jump into the calculus. Whoa, let's take the derivative. Look for critical points. We have 300 minus 3 divided by 4 x squared. Okay, we can certainly set this equal to 0. We get 300 would be equal to 3 over 4 x squared. Put an arrow like this. Now, I can divide everything by 3, multiply everything by 4, and I get that x squared will be 400. The nice thing is we have 20. Well, or negative 20, but that is not in my interval. So this is the only critical point here that's in the interval from 0 to the square root of 1200. What comes next? Verify. There is a verification process that is important and is required for full credit. In particular, this time we're trying to maximize, so I need to make sure I have a maximum here. Because I have one critical point on an open interval, I will, just like in the last one, use the second derivative test. Here, the second derivative, well, we have minus 3 over 2 x. And the second derivative at my critical point, which is 20, is just minus 30, which is certainly negative. Okay, wonderful. This says my function is concave down. So I draw a little picture, concave down. In fact, we do have a max. Now, last part, there's one more part of this. We go back, reread the question. We are asked for the largest possible volume. So you notice, unlike the last question, we were asked for the dimensions. In this one, we are asked for what is the largest possible volume. And, well, here's my volume function. So I need to evaluate this function at 20. My final answer is v of 20, which is 300 times 20 minus 20 cubed divided by 4. This is 6,000 minus, well, this is 8,000 over 4, so minus 2,000, which gives us 4,000. This is our final answer, 4,000. It would be centimeters cubed, but it's fine, just like this. Now we move into indefinite intervals. These are super fun, and I have many indefinite intervals on this quiz extra practice because they are a wonderful practice for us. Now, this first one is basic rules, except I need some algebra first. So what I'm going to do is write this as a sum of two terms. I have 3x cubed divided by 4x, and then plus 1 divided by 4x dx. Now let's simplify each one of these. You notice the first one is 3 over 4 x squared, and the second is 1 over 4 times 1 over x. Now I'm ready to integrate. The first one is power rule. We would have 3 over 4, we add a power, divide by the higher power. The second term is not power rule. If we integrate 1 over x, we have ln absolute value of x. So here we have 1 over 4 ln absolute value of x. Now, maybe because I have 3 divided by 3, maybe I'll write it this way. X cubed over 4 plus 1 over 4 ln absolute value of x plus c. Don't forget the plus c when we are doing indefinite intervals. Next one. This also is basic rules, but I'm going to take a little step first, rewrite this first term as a power. You remember doing this when we were first doing derivatives. If we wanted to use power rule, step 1, rewrite the expression as coefficient times x to a power, and the same thing applies when we're doing integration using the power rule. Okay, well, the first one, we write down the 5, add a power, divide by the higher power. And then this one is a 7. When we integrate 1 over x squared plus 1, this is the tan inverse. Tan inverse. And you notice this is minus 5 over x plus 7 tan inverse of x plus c. This is the second one. Those two did not use substitution. They were just basic rules. Now we move into some intervals that do involve substitution, starting with letter C. Well, you notice here, up inside the exponent v is something more than just an x. We have an x squared. Moreover, we have a multiple of its derivative in our integrand. So this is substitution, where u is what's up inside the exponent, and then du, this will be 2x dx. Now, handed to me in my integral is not 2x dx. I don't have exactly du, but What do I have? I have 1/3 x dx. So you notice, how can I get this from here? Well, let's divide by 2 and also divide by 3. So this is 1/6 du. And you can check. Take this line, multiply through by 1/6. This side becomes 1/6. This side becomes 2/6, which is this. So in fact, I have the correct multiplier here. Now let's keep going with our integral. Okay, so we have an integral, e to the u, and then 1/3 x dx is 1/6 du. Now we integrate. We integrate e to the u. We have e to the u plus c. Final step of substitution is we go back to x, or whatever the original variable is. So here we have 1/6 e to the x squared plus c. This would be our final answer to letter C. Letter D. Once again, we have substitution. You see, we have these big parentheses and something here. This is our inside function. So let me maybe underline the inside function just as I did above. For this one, u is 1 plus the sine of 2x. Let's calculate du. Well, we differentiate. The derivative of 1 is 0. The derivative of sine 2x, really, it's a chain rule. We would have cosine 2x times 2. 2 cosine 2x dx. Now, handed to me in my integral is not exactly du. We have only this, cosine 2x dx. Okay, let's write it. Cosine 2x dx. This is, well, you can just divide the equation above by 2. So this is 1/2 du. Okay, let's convert to an integral of u. We have an integral. You notice this is u to the 4th power, and then times 1/2 du. Now this is something I can definitely integrate. We write down the coefficient, and then we add a power, divide by the higher power. This is power rule, plus c. Our final step, we go back to x here. So this is all together, we have a 1/10, and then we have 1 plus sine of 2x to the 5th power plus c. Integration by substitution. Well, we have 2 more integrals in this quiz extra practice. Once again, in letter E, you see I have something under the radical. This suggests substitution. I mean, moreover, I have exactly its derivative in our integrand, as we will see. So let's write down what's underneath the radical. T to the 5th plus 2t. Just as I did in the earlier examples, I can underline the inside function. T to the 5th plus 2t. Now, take the derivative. du is 5t to the 4th plus 2 times dt. Well, you see I have exactly du in my integral. So I'm ready to just convert. You notice I have an integral u to the 1/3 power times du. Now we integrate by add a power, u to the 4/3, and then divided by 4/3. And the final step, go back to t. And I will typically won't leave a fraction in the denominator like this. So we have a 3/4 t to the 5th plus 2t to the 4/3 plus c. This is our final answer. Letter F. This is the last one, and it's challenging, but at the same time, it's a really good problem. So certainly we see something underneath the radical, which would suggest substitution. However, if you just start writing this, u is 1 minus x squared, du, well, we take the derivative, we have minus 2x dx. What you're left with is the numerator. You see, it's not a multiple of du. I have this sum here. So we will be able to use substitution on part of this. But the first thing we need to do, because of the sum in the numerator, is break this into a sum of 2 integrals. Okay, so this will be an integral. We have 2 over square root 1 minus x squared dx. and then plus the integral of x over the square root of 1 minus x squared dx. Now I'm also going to move this underlined part to here because that's the substitution one. You notice this is not substitution, this is basic rules. We have a sine inverse here. So maybe I will also move this over here. It's really about this second integral. Okay, so this one, as I mentioned, in fact, I'll go ahead and move to the next step. This would be 2 times the sine inverse of x. Okay, I've already taken care of the first integral, but now for the second one. We have u, we have du. This time it will work out. You notice we have a multiple of du in our integrand. So we have x dx. This is minus 1 over 2 du. We can just divide both sides of this equation by -2, and we have x dx is -1/2 du. So the next step in this, I'm still working on this second integral. We have an integral, it's u to the -1/2, that's the power here. And then I have times -1/2 du. I'm already done with this sine inverse part. I'm just going to keep recopying it until I'm finished with the second integral here. Well, let's write down the constant, which is -1/2. And then we add a power, divide by the higher power. Final step, go back to x here. So we have 2 sine inverse of x. You notice this is a 1/2 in the numerator. When I invert and multiply, I'm multiplying by 2. So the coefficient here is just 1. So I have minus, this is the square root of 1 minus x squared. And this is my final answer. That was definitely the most challenging one on this quiz extra practice, but it's a really good one for us to think about and work through. So this is the end of this quiz extra practice, and I thank you so much, students.